Hi, welcome, and thank you for joining our webinar today, Jet Milling and Air Classification, the Secret to Ultrafine Particles. My name is Julie, and I am your facilitator. I'll be monitoring any questions and comments that you may have in the background. We'll have a Q&A session in the end. Before we begin, with me is Kevin Thompson from the American Ceramic Society. A few words from him.
Thank you, Julie, and welcome everyone. I'm Kevin Thompson, the Director of Industry Relations at the American Ceramic Society. Thank you for joining us today for this webinar, which is brought to you in partnership between HORIBA Instruments and the American Ceramic Society, or ACERS. ACERS is a scientific professional society serving nearly 10,000 members who are involved in technical ceramics and glass, and from all around the world. So we welcome you, and hope you learn a lot from today's webinar. For more information about the American Ceramic Society, please visit us at ceramics.org. We do appreciate the opportunity to work with HORIBA Instruments, one of ACER's many corporate partners, to bring you today's webinar. Our presenter today is Dr. Willie Hendrickson, the founder and CEO of the AVEKA Group. Avika was founded in 1994 as a spinoff from 3M. Currently, the Avika Group comprises 5 manufacturing sites and 280 people for industrial, chemical, food, and personal care, contract manufacturing, and process development of particulate materials. Prior to starting Avika, Willie worked at 3M as the technical manager for particle processing in 3M's corporate research facility. He received his PhD from the University of Florida in organometallic synthesis. He is currently the president of the International Fine Particle Institute and has authored or co-authored over 20 technical papers or book chapters. Willie is the current holder of over 50 issued or applied for U.S. patents and will be presenting a plenary lecture at the World Congress in Madrid, Spain in September of 2022 on challenges and opportunities in particle processing. Thank you, Dr. Hendrickson, for today's presentation. And at this time, I'll turn things over to you.
Thank you, Kevin. Thank you, Julie. I appreciate the opportunity to speak today, and thank all of you for joining us today. As Julie said and Kevin said, I'm going to be giving a talk on jet milling and air classification. I'm not sure if I'm going to give you all the secrets to ultrafine particles, but I'll give you some for sure, and hopefully you'll get something out of this. So to get started, what I'm going to do, let's see if we can get to it. I'm going to give you just this outline. I'm going to talk a little bit about Avika, just to give you a little bit more information about what we do, and why we're giving this talk. Going to give an overview of size reduction, overview of classification. We're going to specifically talk about jet milling and air classification, and then I've got lots of examples for you to give you some idea of some of the secrets and tricks to get to those ultrafine particles that we all are interested in. So let's get started here. Aveka Group, where I'm located right now, as Kevin said, we are a particle technology company that does contract manufacturing. We started in 1994, and typically in a year we'll have 300 customers that are in all of these areas, from chemicals to ceramics to aerospace to food. And where we focus on our unit ops that we're actually doing in our contract manufacturing and development processes are, things like spray drying. Size reduction is one of the parts that we're going to talk about today. Agglomeration, microencapsulation, membrane separation. Not only do we do contract manufacturing, but we also do scale up and process development projects. So we get many people, many companies coming to us and asking us, how do I do this? What's the best way to do this? How can I optimize my process? So let's get started then. Let's get right into this short overview of size reduction. We're going to be focusing today on jet milling, but realistically, there's lots of different ways of doing size reduction. If you got big particles, rocks that you might want to start with, you're going to crush them. There's ball milling, hammer milling, and if we really want to get to the ultrafine particles, here's one of the secrets. Jet milling gets you partway there, but bead milling, it's a wet process, would get you all the way there. And maybe in the future, I'll give another talk on bead milling. When you're really looking at what you want to pick, which process you want to pick and how you want to do it, it's all about a number of factors. You know, what's the input size? Obviously, I don't want to put a bowling ball into a bead mill. It doesn't work. You know, what's my final size? Obviously, I'm not going to make submicron particles with a hammer mill. And, you know, what are the distributions, energy efficiencies, and size distribution efficiencies? You know, this energy efficiency is one of the big issues and one of the real starts from a scientific perspective where grinding started. So if we look at this slide here, this is a standard slide. I mean, this has been published many times, where you're looking at the amount of energy it takes to get to a certain size particle, and you can see on the y-axis we're really talking about kilowatt hours per ton of material. And to get large particles, you don't take as much energy, and that's not surprising. But when you get to those ultrafine particles, you really get to that lots of energy that it's going to take to do it. Now, one of the things I want to point out about size reduction, and maybe most of you know this, but size reduction is an incredibly inefficient process. Maybe 2 to 4% of the total energy that you put into grinding something actually goes into breaking particles. The rest goes into heat, the rest goes into friction, the rest just is vanished into the ether. This is a really interesting issue. So anything that we can do to increase the particle size, or excuse me, increase the energy efficiency from 2% to 4%, this is a huge increase. And so doing this right makes a lot of sense. In 1867, von Rittinger first came up with the idea of what is the amount of energy theoretically that you're going to need to do this. And he proposed Rittinger's law. That's the change in energy with respect to change in particle size comes up to basically it's a power law, and it really ends up relating to the increase in surface area. So Rittinger's law really did a good job of explaining energy efficiency and usage. Kick's law does a much better job. This was done afterwards, trying to figure out what's going on. Kick's law was designed or proposed by Kick to actually look at crushing of large particles, where it's not so much the surface area that's important, or the increase in surface area that's important, but it's the plastic deformation of the particles. That didn't fulfill everything, and Bond's law was applied. And when you apply all these different laws with the different power factors, basically you can take just about any material and put it on this graph with the material factor that goes into it, the specific material factor that goes into it, and you can get this relationship that allows you to predict what's it going to take to actually get the grinding of the particles to the size that you want. Now, as I said, material energy, breakage energy is a function of material, and this has to do with the hardness, the bond strength, the plasticity, the crystallinity, but mostly it has to do with the inherent defects or defects that you can actually produce in a system. So inherent defects is where the cracks start, where the breakage starts, and a lot of the energy that you're using to break up these particles is taking these inherent defects and making them to break up the particles, and a lot of the energy is used to produce new defects to actually grind it up more and more to get the finer and finer particles. The other effect that's going to have on this particle size and energy usage is the impact energy. And one of the great things about jet milling that we're going to talk about today is the fact that we're going to use some high pressure air or high pressure steam. So the impact energy is high, which means that we can get to some very small particles. Now, classification is one of these processes that goes hand in glove with particle breakage. And I think we all know that when you break a particle, you don't necessarily get it broken into nice even pieces. It breaks into a wide variety of sizes. And many times those sizes are too small, and you're going to need to classify them out. So typically with most grinding processes, there's going to be a classification process that goes with it. Most of us are familiar with sieves as a way of doing classification, just putting it on a shaker screen and working away at it. But other processes such as elutriation, cyclones, and air classifying that we're going to talk about today have a big effect. As you look at this list that I put in here, basically the bigger particles you're going to do at the top, and the smaller particles you're going to do at the bottom to get air classification is really good in that 1 to 20 micron particle size range. The way air classification works, it's all about balancing airflow against drag. Airflow against drag, and that is combined with the offsetting effects of all these attractive forces, whether it's gravity, electrostatics, van der Waals, magnetics. We're trying to balance all this out and now separate these particles. Now, one of the things that we know about classification is it's not a very perfect process. Let's just call it that. When we use screens, even those aren't perfect, but air classification, you get an efficiency of the classification that depends on the classifier that you use and the materials that you use. Here's an example of a classification followed, a jet milling followed by classification that we did on silica. And what you can see is depending on the rotor speed of the classifier, and we'll talk about this in just a second, you can see that the classification, you can move to different size particles from one size down to the other by changing that rotational speed. What happens is the efficiency is defined as D90 over D10 or D10 over D90 actually. And where you're looking at, the tighter that, or the closer that number is to 1, the tighter the distribution, the sharper this peak is in this particle size here. If you have perfect classification where everything is either above or below a number, you have a D10 over D90 of 1. We'll never see that. You can see these numbers of 0.3, 0.2. This is not a great classification, but for this particular product, this is what we actually got. So let's take a look at the jet mill types. This is what we're going to be talking about today. Jet mills, are not a new technology, but they're not an ancient technology. They were first invented and proposed in 1917 where people were looking at opposed jet milling, basically where you're shooting particles at each other directly. This is with high pressure steam or air. In 1934, fluid beds were invented along with pancake mills, and then finally oval jets in 1940. Now, the difference between all these processes is that the opposed jet and fluid bed always have a separate classifier, a separate unique classifier, whereas pancake mills and oval jets have an inherent classifier. And I'll show you this in just a second. So this is a schematic of an oval jet where particles are coming in from the right side here. Your raw feed is coming in. You have some high pressure air nozzles at the bottom, and what happens is that this is basically a cyclonic action where the particles are being pushed around the system. They come down to the grinding zone at the bottom where the nozzles are. The particles are bounced off each other and off the walls. They break up, and as the particles get smaller, the air cycles around just like a cyclone, and eventually the fine particles can leave the system. Now, with a pancake mill and an oval jet system, because it's inherent to the system, you have some problem controlling that particle size distribution, and you end up with less control than you would have on a fluidized bed jet mill or a pancake mill. So let's show you the schematic of a fluidized bed jet mill, and this is what we're going to be talking about today, the fluidized bed jet mill. Avika makes these mills. We sell these mills along with the classifiers that go with them. And basically what you have is you have a grinding chamber down at the bottom where you have, in our case, we have 3 high pressure jets that are blowing into the system. The particles are loaded into this fluidized bed. They're grinding in this area. And when they get small enough, they're air entrained up to the top, and they go through this classifier, basically this rotating wheel up here. And the smaller particles will go through at higher rotational speed of the classifier, the bigger particles get pushed back down to be ground up. And so basically what you're doing is you're removing the product, the fines, out of the system as fast as you can. This allows us to get a tighter cut and better utilization of the material. Just to give you a little bit different view of this, this is a CAD drawing that we have of the system. You can see right here that the classifier wheel that's going into the system. And as it all comes together here, we're going to get this cross section. And I just want to stop here. This is our classifier wheel, and as this spins faster, we can cut at a smaller particle size. If it spins slower, we're going to cut at a larger particle size. If you actually allow this all to work, what you're doing down here is you're having your fluidized bed down at the bottom where the grinding is going on. The particles are coming up to the top, and let's just stop this for a second. Particles are coming up to the top and then leaving the system. Now this is a cross section of a separate classifier, and we'll just stop it. Oh, just didn't stop at the right spot. I never do this right. We stop right here. What we have here is this is the classifier wheel, but instead of being horizontal, it's or vertical, it's horizontal. The same sort of idea. It's just a larger wheel, allows us to get tighter cuts, better cut action. And so this is the annulus ring that allows the particles to sweep around the system. And when they're small enough, they'll go through the system and leave the system. And just by changing the airflow and the rotor speed, it allows us to get the type of classification that we're actually looking at. So, you know, these are the jet mills and classifiers that we're going to talk about today. The types of materials that you can actually jet mill that are commonly done, you know, range from ceramics to metals to glass to diamonds to food to carbon black to cosmetics. I mean, there's just about everything in the world, and I'm going to give you lots of examples in just a few minutes of some of these materials that we've classified. The interesting thing about this, and I want to point out, you know, the things like the glasses, the ceramics, the diamonds, the minerals, these are highly abrasive materials. So we typically, jet mills will typically be lined with an abrasive resistant material. It could be another ceramic or it could be a polyurethane. The other thing that gets interesting when you're dealing with things like polymers, drugs, carbon blacks, cosmetics, foods, these all have the potential to explode. And this is one of the challenges about jet milling and air classification, because you're making fine particles that are going to be more and more explosive as they get finer and finer. So the way that people deal with this, you know, this has been going on for quite a while now, is you explosion suppress the systems. Very difficult to do this in an inert atmosphere. I've heard of it, but typically jet milling air classification is done with explosion suppressed systems. So that's important that you realize that you can do materials that have had inherent explosivity, that you can actually deal with them in these systems. Just to give you schematically how a fluid bed system is set up, and this is important for you to think about. Here's your fluid bed, here's a feeder, it's set up to a collection bag house, and this is just the air exhaust that are pumping the air through here. What's important about this, what makes jet milling to me very interesting, is the way the system operates. It's all done under negative pressure. So the chance of materials leaking out, unless there's a process upset, are very small. So you can have very nice controllable environments for your workers to work in and not have this issue of a dusty environment. I really like these jet mills for that purpose. This is a schematic of the classifier hooked up to an opposed jet mill, opposed dual jet mill. In this particular case, the particles that have been ground entered the classifier. They go around the system. The fines cut comes out here, and the coarse cut goes back in the system, and then you can add continual feed in the system. This allows you to you know, you can set this up without a jet mill, where you're just feeding feed in and then no recycle. It's just a way of having a double classifier on your jet mill. So with all of that, let's actually look at some of the examples that we have here. And I'm going to start out with what I consider the classic jet milling air classification combination. In this case, what we're going to do is we're going to take a starting material. This is a specific ceramic that's used in abrasives. We're going to actually take this 177 micron particle size particle. This is the median size. And what we're going to do is we're going to grind this material at different conditions where we're going to remove the fines, the product that we want, and then classify it in the second step. Once again, you know, the coarse material that hasn't got down to the right size gets pushed back in the system and remains until it's in there. And the idea here is we're going to remove fines in two-step process. First in the jet milling with the classifier, and then in the second step. So let's just take a look at what happens when we do grinding with a low rotor speed. And the low rotor speed is that classification system at the top of the jet mill. In this particular case, we took that 177 micron average particle size down to 34 microns, and we got a distribution that looks like this on the right side of the screen. Now, the interesting part about this is you notice that this is a fairly broad distribution, and for abrasives, that's not a good situation. You want a tight distribution. So we're going to want to classify this again. When we went to a higher rotor speed, I mean, I think this is at about 200 RPMs, and this is at about 800 RPMs. And the difference is we go from a 34 micron to a 14 micron cut, a little tighter distribution than we saw on the bigger speed, but still too many fines on the end of this thing. So what we're going to do is let's first look at the SCM. So what we have here, this is the raw material. It had a D10 to D90 of about 200 microns, 86 to 285 microns, big particles. After our first grind on this stuff, on that coarse grind, where we're doing the low rotor speed, we got a particles distribution of, I believe it was 34 microns, and the distribution went from 7.2 up to 65.9. If we go to the finer grind, where it's a higher rotor speed, so we're classifying, we're doing more grinding on this system, you can see the particles have gotten smaller, but look at all those fines that are in there. I mean, it's an incredible amount of fines. So what we did is we now took these materials, each separately, the coarse grind and the fine grind, and we sent them over to our classifier, and you can see the classification is much, much tighter. We got rid of the fines, all of the fines in the coarse cut, and most of the fines in the fine cut. And we changed that average size distribution from a 73, a 34 up to a 73, and a 14 up to a 19. Now, you might ask the question, why didn't we grind at a higher particle size so we could get more product out of here? Because obviously we're cutting on the one edge of the particle size distribution. And the reason that we did this is with abrasives, you don't want a lot of large particles. So what you're going to do is you're going to actually, you know, get rid of the large particles, cut your yield down a little bit, and you know, end up with a tight distribution like this. Just to show you what this looks like from an SCM, this is, remember all the fines that were in the coarse product and the fine product, and they're all gone. This is a nice tight distribution for an abrasive application. Really worked out nicely. And this once again, this is a classic jet milling air classification two-step process to get this type of tight distribution. Now let's take a look at something where we're just going to look at jet milling and compare it to a different technique, ball milling. So what we're doing here is we're grinding zirconia sand. So this is a rather big particle to start with. And what we're looking at, what happens with a jet milling process or a ball milling process. Now, if you look at the bottom of the screen here, you see that the D50 is about the same size, 6.3 to 6.6. You know, we were actually able to kind of hit the right process here, but you can see On the ball milling, it seems to be a much broader distribution, and there seems to be a lot more fines on there, which is exactly what it is. So let's just take a look at the SEM images here. Here's our sand. I mean, it really is sand. I mean, these are sand granules. And if you look at the ball mill SEM picture here, you can see we've got the right size, but lots of fines. And so, you know, in this particular case, as opposed to the jet milling situation, in this particular case, even though you could get the right size with ball milling, which is a cheaper process to use, by the way, I don't discount ball milling as a great way to do it. But if fines were an issue, and they were in this particular case, jet milling turned out to be the better process. That's just kind of given us this idea of why we would want to do jet milling if it is more expensive, but because we can actually, you know, control that size distribution and do a little bit better on that fines generation. Now let's just consider classification for a second. No, there's no bead milling or no jet milling in this particular case. And basically what we're doing is we're taking nice spherical glass beads, and we want to classify out and get that distribution, get rid of that fine cut again, because we didn't want the fines. But what we want to show here is how can we optimize the yield after classification. So the tighter that we try to make our distribution, the finer that distribution, the more product that we're going to be let go. So here the starting glass has a D50 of 33 microns and a D10 of 19 and 48 microns, as you can see on this slide here. If we go to a broad classification, and broad is really not that broad, we're going from 24 microns to 50 microns, about the same D50 particle size. And if we go to a tighter distribution, 25 microns to 48. So that's a 3 micron difference in the distribution of this product. We're cutting right in the middle of this thing. We're cutting this end off here. And all that we're doing is we're cutting just a little bit tighter in one versus the other. You know, my first look is when we set out to do this is I was thinking we're really not going to see that much of a change in the yield. But let's take a look at the next slide and see what actually happens. Here's the SEM picture, so you can see that the fine and the narrow cut look about the same, maybe a few smaller particles in there, but look at the yield on the broad cut versus the narrow cut. A 3 micron difference is almost double the yield of this. I put this example in here for everybody to understand that being a little flexible on what process parameters that you want, what final product parameters that you want, can have an incredible effect on the final yields. Many times we have people come in that they've identified that they want this narrow cut and won't look at what happens if we just broaden it out a little bit, but the effects can be spectacular. Well, let's consider grinding of a polymer. This is a material. This is an engineered plastic that's used for additive manufacturing. And in this particular case, we jet milled the polymer, and I'm giving you 2 particle size distributions here. One is a volume distribution, standard sort of volume distribution. You can see most of the product is in the size range that we want, that 100 to 50 microns. But what we found when we classified it, we still had to get rid of these fines because the fines just changed the flow characteristics of the material to an adverse effect. And so we classified out the fines, and we did many different test classifications, and we got rid of the fines all the time. But we were getting all these variable results that we couldn't actually understand what was going on until we went and looked at the number distribution. So instead of looking at the number of volume in each one of these bins, we were looking at the number of particles. I do want to point out in deference to HORIBA for setting this up, all these particle size distributions that I'm providing here are HORIBA, done on our HORIBA systems. If you don't have a HORIBA, please buy one, they're great. But the issue here is that if I had one 100 micron particle and I were to break it up into one micron particle, I would have that one, or break it up into 1 micron particles. I would take that one particle and I would make 1 million particles out of this. It's an incredible change. And you can see that even though we have the big volume in the size that we want, the number of particles in the fines is just incredible. So what we did is we now, in this particular case, we were analyzing our jet milling and classifying with number distribution, and we have a specific spec that calls out that all of the particles need to be less than 1% below 20 microns. And you can see we did that, and now we could actually differentiate what the jet milling and air classification processes that would actually give us the right number, the right functional results in the flowability. So here's some SEM pictures of the polymer. This is a solution cast polymer. I always think it looks like a potato, and after we grind it up, you can see a lot of the fines in here. And after we classify it, we clean out all those fines, and we get the product that the customer wanted. Now, one of the real interesting things about all of this processing is that with grinding, many times you have to do this in multiple steps. This is an example here where we received sheets of glass, and these sheets are big, but they want it ground up to around 5 microns. If we put sheets of glass in a jet mill, nothing would happen. So what we did in this particular case is we did a two-step process, a two-step crushing and jet milling. And this is the type of crusher that we used. It's a finger crusher, and basically you pour that material in there, and those fingers just crush that glass up to get this feed material to our jet mill. Sheets that are much bigger than what you're seeing here. I mean, they might be feet in diameter, going to a nice feed that we can now feed into our system, ultimately to get the final product that comes out of here. What happens is by doing this, instead of it taking hours and days and years to grind up material, we can do this in a very fast and facile fashion. So this is the results that we get. We were taking these big pieces of glass, grinding them down to a nice tight distribution, around 5.3 microns, and here's the SEM picture that we actually get in a situation like this. So really, thinking about how you want to approach this, we have many examples where we're doing not 1, not 2, not 3, but sometimes 4 different grinding steps to get the optimum yield of the right size particle at the lowest energy usage. I have another example here just to show you another two-step crushing and grinding process where we were asked to grind up a carbon material. And this is a carbon, and I'm saying carbon because it could be graphite, it could be carbon black, it could be a number of different things. And these are used in battery applications where we first jaw crush the material. And then finally, after we jaw crush the material, we had these big lumps that we started with, as shown here on the left side or the right side of the screen. And we were actually able to feed that fine powder into the jet mill to get a distribution that looks like this. So this is not quite as fine as the glass product. It wasn't needed to be as fine. We could have actually ground it to a finer size and classified it tighter, but you can see that we've gone from things that you're not going to measure with the laser diffraction system to a nice distribution. I just want to emphasize again the importance of having a good grinding process, multiple step, because otherwise sometimes it just doesn't work. Taking it stepwise is one of those true secrets that is in the grinding world. So I have a couple different grinding and classifying final examples here for you to take a look at. This first one is a two-step classification of silica. And you can see the raw material that we received is about 11 microns. So it's a pretty tight distribution to start with. But once again, there was a few too many fines in the system, and our customer wanted us to take the fines out, but really maximize the amount of yield that we have. And so this is an interesting problem. Rather than cutting into the middle of the distribution, we're basically going to nibble at the edges. We're going to take out just as few amount of material as possible. And so we did this first classification. We went from 10 almost 11 microns up to 11.5 microns, just by cutting a very small shoulder off the small end of this system. As it turned out, we didn't get the result that we wanted. There was still an incredible amount of fines that were in there. So we did a second pass with the second little nibble on the system. And the results that you can't see here with the particle size distribution, I want to show you on this next slide. So here's our raw material, our silica raw material. You can see a lot of the fines in the system. The first class pass classification, there's still fines in there. I mean, you know, this was kind of surprising. We thought we'd get most of those fines out, but surprisingly, with the second pass classification, we took out all the fines. Now, I think this is one of the real challenges of particle processing, and I want to spend a little bit of time on this to really impress upon all of us the difficulty of particle processing, and in this particular case, this classification. Inherently, logically, we would not expect to see this big change from the first and second class classification, and yet it happened. And this we see again and again and again in particle processing. We find out that the fines that are inherent in almost every material almost need to be stirred up again and again and again. And when you do flow measurements, dry powder flow measurements, you see the same effect going on. And here we're seeing it in grinding. I'm not sure that I completely understand it. I'm not sure the people that do flow measurements completely understand it, but I can guarantee you that this is one of those big issues in particle processing. And here we have visual kind of affirmation of the importance of maybe trying it again and seeing what happens if you stir it up. And in this particular case, that the change of the fines from the first to the second, I think is incredible. So finally, my last example that I want to give you is one that's completely different. We're gonna go back and compare ball milling and jet milling, but we're gonna grind up fibers. And this was an interesting question for us. We had a customer come to us and said, what happens when you grind up cellulose with a ball mill, and what happens when you grind it up with a jet mill? One would think that you're going to get smaller size. I mean, and that's what we want. So the pictures that we have here show cellulose, dried cellulose fiber. This is wood. This is wood pulp cellulose. And just for those of you that don't know what cellulose, the structure of cellulose, and this is important to know, cellulose is typically a tube. This is where the water flows up in a plant, whether it's wood or a vegetable type plant. And these things are hollow, and the walls of the fiber themselves actually are like a belted bias tire, where there's multiple microfibrils of cellulose that form this structure. And so it basically looks like a belted tire, a bias belted tire. These holes that I'm showing here, these are actually the ports that water enters and leaves fibers, and it was interesting that we were actually able to see this. Now, so what we did is we started out first and we ball milled the material. I'm going to show you the pictures on this next slide. So once again, I have the untreated fiber here. You can see it here. And after ball milling, basically we see size reduction. I mean, there's breakage of these fibers, ripping, I would almost think. But also, if you looked very carefully at this, and you can't see it completely on this, but what happens is a lot of these fibers are just folded over. And so it's like folding your clothes and stacking them up. And so it gets smaller and smaller. The particles get smaller. There's some breakage, but it's a lot of folding. But now when we take this ball milled fiber here and we jet mill it, we get this structure. And what we're doing here is we're actually fibrillating the structure, and we're we're actually forming this, we're actually exposing the microfibrils that are in the cellulose fiber here to get this structure. One of the questions that you should ask is, who cares? I mean, you know, it's interesting, it's an interesting picture, but from a functional characteristic, these results and the grinding results were incredibly revealing. In the case of what the customer was interested in was how much water could a fiber hold. And it was cellulose fiber, you could hold about 2 times the weight of water. So if I had a pound of cellulose fiber, I could hold about 2 pounds of water in there and it wouldn't drip. But now if I took this ball milled fiber, it drops down to about 1. And you can kind of see it. You know, there's not as much capillary opportunity here, and you know, kind of push this all together. But now when we look at the water holding capacity of this jet milled fiber, it actually holds about 10 times the amount of weight. So a dramatic change depending on what structure that we have here. Now we didn't really measure particle size here. It was a little difficult to do that, nor did we classify this material because it was a little bit difficult to do it. But yeah, I thought that this was an interesting example to end with, that the jet milling that you can do on these things, it's not just about particle size reduction, it's not just about distribution, but it can be about the actual form and structure of the materials that you make. So I have just my last slide here, my summary slide. You know, hopefully I've given you some idea of what jet milling and air classification can do for you for lots of different materials and lots of different industries, whether it's a battery application, an additive manufacturing application, you know, whether it's a ceramic, a polymer, a fiber, you know, you can get some good tight distributions at 75, you know, 1 to 75 microns. Optimization of the processes might require you to do a couple steps. This is one of the big secrets of all of these things, of, you know, how are you going to get this, whether you might need 2 grinding steps or 2 different grinding steps, or you might need to classify once or twice or 3 times in order to get what you want. The final results, I mean, I think we've seen this with the different materials, incredibly material dependent. I mean, obviously with the fibers it is, but even on the ceramics, the glasses, the polymers, each of them you have to kind of work your way at. And it just leave you with this final thought, is that you're going to need some tricks to really get this thing to understand, to get that optimum final product. And what that trick is, you know, who knows, because it depends on what functionally you're looking for, what distributions you're looking for. But it's one of the things that, you know, makes grinding and classifying really worthwhile. You know, I'd like to thank you all for listening. You know, as a company, you know, we love to do this stuff, from the R&D scale to manufacturing to partnerships. And I surely welcome any questions. And once again, thank you all for listening.
Well, and thank you, Willie, for the excellent talk. For those of you who follow Willie from one webinar to another, the next one is going to be on October 19th on characterization. All right, so a few questions that came in. Is it possible to generate a constant concentration of carbon particles at least for 3 to 4 hours time? And we're talking about the concentrations, number of particles per cubic centimeters.
What was it? They want a constant concentration of particles in what? In air and water and liquid?
Let's see. Didn't say. Is it possible to generate a constant concentration of carbon particles at least for 3 to 4 hours time? 5 nanometer to 500 nanometer size, and max
So
concentrations 50,000.
Julie, let's pretend that it's going to be in a liquid
Okay.
basis.
Oh, air. I'm sorry. He just added in air.
In air. Let's pretend that it's in air. Let's not pretend. Let's actually say that it's in air. I presume that this is this, boy, it's a great question. The answer is, can I have a constant density of Aveka particles? The answer is yes. Can I actually disperse these particles and keep them in air at disperse them so they're floating in air? We're now faced with Stokes settling. So if they're nanoparticles, we've got a chance to keep them in air. Just Brownian motion would keep them. But boy, once you get above about a tenth of a micron, they're going to be settling pretty fast.
Thank you. Yeah, we do have a lot of ultrafine particles related questions for sure. This person said the cellulose fiber example is very interesting, so thank you. The next question is, in the example that showed first pass of classification to second pass of classification when trying to remove fines, did any settings change between those two passes?
Yes, obviously. So every, to take a little bit more out, we probably would have. Well, that's a great question. The answer is yes. We would have decreased the rotor speed to allow us to take a little bit bigger cut, a little bit larger size. So is the question is, could that affect why we're seeing this change? Possibly. I don't think so, but anything's possible because we don't have the answer just yet.
Thank you. Can you comment on how particle aspect ratio varies with jet mill operating parameters and how ball mill compares with jet mill in this aspect?
I'm being stumped one after another here. I can't
Sorry.
believe it. We don't necessarily see an effect of aspect ratio on the parameters that we use. Not that we've looked that hard at it. Boy, that's a great question. I mean, that in jet milling, because particles are flowing in air, there's going to be some alignment. So you could imagine if you had needles versus spheres, you would see different classification, different jet milling. Man, oh man, that's a great question. I would really like to have some time to sit down and talk with this person to see if there's something more to the question, because it is a great question. I don't know that I've seen a difference though between the ball milling and jet milling from an aspect ratio.
Yeah, it's quite interesting. Is it a 1-to-3 ratio? Is it 1-to-5? And so definitely these questions will get passed over to Willie and also Kevin as well. So we can follow up with you later on. And you can also email us at labinfo@horiba.com, and I'll put that in the chat box as well right now at horiba.com. Okay, so the next question is, can jet milling work for a dry powder blending operation?
That's a question I can answer.
Yes.
Yes, it can be done. I actually had a picture I didn't put in this slide where we actually had two separate feeders that were feeding in materials to the input of the jet mill, and we came out with a very nicely blended product, a jet milled and blended product. So yes, it can be done.
Can we mill the particles to less than 10 nanometers?
Wow, that's a great question. So the answer to that is not with a jet mill. To my knowledge, I've never heard of anybody mill a particle typically below 1 micron and maybe occasionally to 0.7 of a micron. If you wanted to get to a 10 nanometer particle, a jet mill material might be a great feed, once again, in this multiple step grinding process. The process that I would typically use to get to a 10 nanometer particle would be bead milling.
Thank you.
I don't think jet milling is going to get you there.
Next question. How does impurity pickup differ? How does impurity pickup the difference between jet milling and other milling processes, assuming you are milling a highly abrasive material?
I'm sorry, what was the one word? How does a something?
Impurity.
Oh,
How does
impurity.
impurity pick up difference between jet milling and other milling processes?
Yeah, I mean that's a good question. So typically, what we talk about milling processes, we call them media milling processes and media-less milling processes. If you have a media milling process, that's a ball mill or a bead mill, there's always going to be wear of the media, and that's going to be a contamination in your material. With the media-less process, there's no media to wear off and get into your product as an impurity, but there is going to be wear on this from the sides of the walls. So if you wanted a lower, this is typical now, and you know, there can be all kinds of differences depending on specifics of materials and processes and everything. But typically, if you want to minimize impurities, I would consider a jet milling process. If impurities are less of an issue, a ball milling would be a way to go in that direction. But I can tell you from the wear that we see in our jet mills, particularly with abrasive materials, there must be impurities in there because my jet mill is wearing away very quickly. So maybe less in jet mills than in a ball mill, but still there's going to be the possibility of impurities.
Thank you. Okay, the next one is one of my personal favorite, pharma question. Is it possible to mill pharmaceutical drugs from 10 microns to 1 microns with narrow distribution? And what do you prefer, jet or ball or wet milling?
Good question. You know, I would say that with a fluidized bed jet mill and an air classifier, you know, going from 10 microns to 1 micron, and once again, it's very material specific. If it's a soft material, it might bounce around in there. But if it's got some crystallinity, getting it down to 1 micron from 10 microns, very reasonable thing to consider. And with that second classifier, I think you could have a tighter distribution than you could have with either a ball mill or a pancake jet mill. I think you could get much tighter with a fluidized bed jet mill with a secondary classifier.
Very, very specific. Thank you. Okay, next question. What about jet milling of polymer? Do you use any coolants?
No, we don't. And that's a great question. This is the second time within a month I've been asked, do you do cryo jet milling? I mean, that would be the question. And the thing is, there is so much air going through the system. We do not see an appreciable rise in the temperature of the product during jet milling. So, you know, there's two reasons to add coolant, liquid nitrogen to grind materials. One is to just keep the temperature down so you don't actually melt your material while you're grinding. And now we're typically talking a hammer milling process. But the other reason is that you put liquid nitrogen in the system to embrittle the material, the polymer. But with jet milling, there's so much air, it would heat up so rapidly, you would reach ambient air temperature very quickly. I don't think doing a cryo jet milling actually would make any sense. Now, having said that, I could be proven wrong 100 times, and I'll be astounded. But I would guess that, you know, I know that we don't add coolant because there's so much air in there, it doesn't heat up. And if you need to embrittle it, we probably have to consider different processes.
Thank you. Is it possible to jet mill and classify hard materials such as silicon carbide into submicron size without having any cross-contamination?
Oh, we have ground silicon carbide. We've ground many materials, you know, but considering the fact that my jet mills or other people's mills, whether it's a media mill or a different type of jet mill, there's always the chance of cross contamination, impurities. What I would say, if it turned out that impurities were just the killer of all killers, we would probably line our chamber and our contact points in our mills and classifiers with silicon carbide. So if there was contamination, it would be silicon carbide. So, maybe the answer is you can do it. You're just going to have to set your mill up properly to do it.
Which of the jet milling types will add the least amount of contamination to the feedstock?
Oh, I don't know that I've ever looked at that. I mean, like, I know that there's going to be, there is going to be wear in every single one of them. And if I had to pick the one, I would say that the processes that don't use the classifier, the squirrel cage classifier, that's where a lot of the wear actually occurs. So, if contamination was really the driving force for you, you might go to a pancake mill. I mean, that might be the best way to go, but I know that they wear too. So, I think your best bet is if you can put some hardened surfaces on there, some ceramic surfaces or silicon carbide, something that would be appropriate. But they're all going to have some contamination. But if I had to take a guess, I would go to the pancake mill for least contamination. And that's a guess, though. That really is a guess.
Thank you. Okay, so in the interest of time, I'll ask one more question. What is Avika's production capacity for jet milling? I know it can change based on materials. Air rate may be best way to illustrate.
So thank you for that question, whoever asked it. We have mills that are small that we can do a pound of material or even less than a pound of material. We also, on a regular basis, will grind up truckloads of material, 40,000 pounds in 2 or 3 days. So, we have a lot of capacity, and we have bigger mills that we haven't set up that could even do more. So, I would say, pounds to multiple truckloads, per week would be very, very reasonable to consider.
Thank you, Willie. There's so many questions that we might have to take it offline and answer as we go through the list of questions later on. I do want to honor your time and honor Kevin's time. Again, don't hesitate to write your questions to labinfo@horiba.com. If you have any feedback, I would love to hear it too. Thank you, Willie. Maybe we'll have to do another one of these jet milling classifications. Seems like a very hot topic. But for now, on behalf of our particle group, thank you so much for attending, and don't miss the next webinar that Willie will be giving sometime in October. All right. Thank you so much, Willie. Thank you, Kevin.
Oh, thank you. Thanks, Willie. Great talk. And thank you, Julie and HORIBA for partnering with us on this.
Sounds good. Bye for now.